Well, hello everybody. MoNaCo here.
And notes.
We're in video 3, homework video 3, so there's a little 3 at the top of your page.
Yep, should be on page 7 and 8.
And 8, same video, 2 pages.
Woohoo.
We're talking about some things here, about energy and how it works within our unit. And we're going to see how it interacts with matter. So we're going to probably focus on things like kinetic energy, potential energy. What do we got here?
Yeah, well, first we're going to start to redefine some of those words that we've heard of.
Right.
We've been working on it the past 2 days, or past 2 videos.
Working definitions, and we're really focusing on what is the difference between kinetic energy, heat, and temperature, because I was saying before how these are kind of all related, but we got to know how they're related and how they're not related, like comparing and
Right,
contrasting.
so if we can differentiate them,
Yeah,
we can understand them a little bit better.
sure. Let's
Alright,
give
cool.
it a shot.
Let's do it. First, 2 main types of energy. First one being kinetic,
Energy, yeah.
which
heat.
is heat. And this is the energy that causes our molecules to move.
Right, the energy of motion. And as a matter of fact, chemistry itself, overarching theme, is the study of matter, atoms and stuff, molecules, and energy, kinetic energy, heat energy, and how they interact. So this is really a really gigantic part of chemistry.
Yeah. And it gets to be predictable. If I raise the heat, then
the motion of the atoms will increase, decrease, etc., whatever. Right? Okay, so kinetic energy has 3 types, and this is Mr. Milk's wheelhouse, so I'm going to let him take this one.
I'm going to do the middle one first because that's the one I think we know the best. But these are the 3 kinds of motion that exist, right? Translational motion is really the motion from one location to another. So from point A to point B. You know, you go from chemistry class to history class. You just did some translational motion. You might know it from math class when you had to translate across the y-axis.
Geometry or something like
Yeah,
that,
when we're doing those graphing of, triangles and
You
stuff.
slide the whole picture to the right.
Right.
Slide to the left. Now we're talking about actual points.
Right.
Particles in motion.
Now this is something we could imagine in a gas or a liquid. If we were to increase the kinetic energy, this motion would go farther, faster. Right. So this is a major piece of motion that we need to understand.
Right.
Okay. Now, this is going to be for liquids and gases. Of course, solids don't really have translational motion because the molecules or particles are fixed. Their potential energy is less. But what we do have is sometimes rotational motion, which will also be liquids and gases. I guess I'm jumping the gun on the solids thing.
Right.
So rotational motion is basically the molecule is no longer moving from point A to point B. It's staying at point A, but it's spinning.
See if I can do this.
There you go. It's rotating around an axis, kind of like the Earth is, except for think about the Earth stopping revolving around the sun.
It's
So,
like,
right.
It's got an axis, right?
Yeah, right down the, there you go.
So it's
Beautiful.
like rotating on an axis.
Right, but it's not moving from point A to point B. It's staying fixed at point A. All right, and so it can do that. Now, liquids can do that.
Could
Right.
an atom or molecule roll from point A to point B?
But then it would have both.
Okay, nice.
Yeah, now, all these kind of motions happen simultaneously.
Are currently happening.
Sure. Vibrational motion. Now, this is that wobbling back and forth, if you will, vibrating without spinning.
I got my particle.
And then, I don't know, back and forth little arrows, small? No, around, though. Yeah, around.
It's kind of all just
Okay.
vibrating up and down,
Sure.
left and right, in and out.
Yep.
maybe?
Yeah, I was thinking about maybe making it circle around, kind of back and forth with an arrow.
Right, so it's vibrating on all possible axes.
Yeah, it's not completely rotating, though. It's just kind of vibrating. Okay, now this is what...
Vibrate from point A to point B as you roll,
No. Because now vibrational motion specifically
or
solids.
solids.
Now, when we say the desk that you're sitting at is moving, this is what we're getting at. The molecules within the desk
Are vibrating in place.
are vibrating in place.
If they were moving translationally, they would be all of a sudden not under your butt holding it up.
Yeah, they would. Yeah, I mean, you think about that. It would basically be melting.
Right.
All right. So the reason why I know that there is vibrational motion is that it's not at absolute zero.
It has
Some
heat.
latent heat in it.
So the atoms must be moving.
Yes.
It's kind
Just
of the nature
it's a
of
different kind of
universe.
moving.
Yeah.
So we just want to get that fundamental piece out of the way because it's
so liquids and gases do translational and rotational. Solids pretty much just vibrational.
That's all they can do. Yes.
Yeah. Because if they were moving, then they wouldn't really be solids. They would be liquids or gases.
Yeah, they need to be in that fixed space.
Yep. Now, potential energy. It's the energy of position. For us, it relates to phase change. It's just like how much energy is stored up in the solid phase. And the weird thing about potential energy is you can't measure it unless it changes. As a matter of fact, with any energy itself, you can't measure it unless it changes. So I can't tell you how much potential energy is in this ice cube, because in order to find out, I'd have to turn it into not an ice cube anymore. And it's difficult to do.
Sure.
We don't have to actually quantify potential energy, this unit. So for us, all you really got to know is that potential energy is changing when one of the principal forms of kinetic energy is changing. So like from a solid to a liquid, it's going from that vibrational energy to that rotational translational energy. Potential energy is involved there.
Right.
Because it's the energy about position. The atoms are locked in a specific spot. They're pent up with tons of potential energy, and then they turn and melt into the liquid phase. Potential energy change there.
Right. The potential energy is taking that kinetic energy and like changing it into a different form of energy to help it change phase.
Right. The phase transition is taking kinetic energy and using it to change that principal type of motion from vibrational to rotational to translational, so that the atoms and molecules can begin to move past each other and no longer are in that solid, the liquid, or the gas phase.
Right.
And the weird thing about this when we do heating and cooling curves is you're going to see that the temperature, average kinetic energy, doesn't change when this happens.
Yeah,
all the energy and all the heat involved goes into changing the potential energy, and we're going to hit that more up later. Heat flow.
So again, always from hot to cold.
Right.
There's no such thing as from cold to hot.
We've got some cool little demos that we can try and show you on this with some metal bars and grabbing the hot cup and the cold cup and all that stuff. When you feel cold, it's a sensation thing. It's not an actual energy thing. When you feel hot, it's a sensation thing. That is more related to energy. But if it's hot on the in the house and you open up the window in the winter,
the cold doesn't come in.
It's the hot leaving.
Yes.
And you feel the absence of the hot as cold.
You can almost see it sometimes when it's hot on the road. You know, you can see the
wavy lines above the car hoods and hot. Yeah.
Yep. You can see it sometimes.
That's an optical effect for other reasons, but it is related to motion of
and with heat
and flowing. It is moving.
So heat is not the same as temperature. We talked about this
earlier. That was
one
of my bullets that I wanted you to write.
And we're going to hit it again and again. Heat is specifically kinetic energy.
Right. So
and
temperature is specifically measurement of the kinetic energy.
Right. It's specifically the average kinetic energy. We say the average because not every molecule is going to have the exact same energy. Some, in fact, are going to have enough energy to escape and change phase at the surface and go from liquid to solid or liquid to gas.
The cool thing about heat is that you can't actually measure it without measuring a change in temperature.
Right. So next, absolute zero.
It's the temperature at which all motion stops. So like all atomic motion is theorized to just completely end at absolute zero. This doesn't, well, it hasn't been attained yet by us humans here on this planet. And
we've been able to stop the translational motion. We've been able to stop the rotational motion.
But the vibrational motion of atoms,
never been able to stop.
Never been able to stop. You get them down to that temperature almost. You can, if you could look at them with an electron microscope, they'd still be zipping around, wobbling around, going, "Hey,
vibrating.
I got energy still."
Right, because they have some amount of heat. So that's the main reason why we had to talk about those three kinds of energy. Motions.
Absolute zero really comes into play when we're talking about temperature conversions and Kelvin and Celsius.
Right, and what Kelvin does, because of these three kinds of energy, or this motion, if you will, Kelvin gives us this spectrum of all total energy.
Right.
Not just the freezing point and boiling point of water, which is Celsius.
Kelvin
this talks about all energy.
Kelvin temperature is most directly related to that kinetic energy, the motion of atoms. Absolute zero talks about 0 Kelvin, and 0 Kelvin means there's no heat energy involved. So and therefore there would be no motion energy involved.
Correct. So
and as
we-
we said, that's not
Right,
really
we're going to
happened yet.
expand this. We're going to expand the spectrum.
Yes.
So that's why we use this in our energy calculations. We have to use Kelvin to talk about the total energy. So this scale is going to encompass that total energy.
Sure. Sure. Total kinetic energy.
Sure.
So some temperature conversions. There is a special reference table, table T. It's got an equation on it. Kelvin equals degrees Celsius plus 273. So you will be asked to convert temperatures from Celsius to Kelvin.
Sure.
Straight up algebra, plug and chug. I'm going to convert the first temperature 0 degrees Celsius into Kelvin. And watch how I do. I write my Kelvin equals, and I'm going to put in the degrees Celsius, 0 degrees Celsius plus 273. So when I do my algebra there, I realize that, well, that equals 273 Kelvin. So 0 degrees Celsius equals 273 Kelvin.
Beautiful. Once you do the next one, I'll do the next two.
Okay. The next one I'm going to do is another very common degrees in Celsius that we got to convert to Kelvin. Kelvin equals, I'm going to do 100 degrees Celsius. So 100 degrees Celsius, the boiling point of water, plus 273. And we see that if I add 100 to 273, that's 373 Kelvin. So again, 100 degrees Celsius equals 373 degrees Kelvin. Different units for the same amount of average kinetic energy.
And then you know how we do things in chemistry. If I can do it forwards, I got to be able to do it backwards. So do you think I should rearrange the equation first or no?
I don't know. I would use the equation like our students would use it. Just
All right, sweet. Just plug and chug it right in. All right, so here, one of the most common Kelvin temperatures we get is 298. So 298 kelvins is going to equal some degrees Celsius plus 273. So in order to solve this algebraically, I need to subtract 273 from both sides. Once I do that, I will get a Celsius temperature of 25 degrees Celsius.
Yep.
So 298 kelvins really equals 25 degrees Celsius.
So again, it's the same amount of average kinetic energy measured on two different scales.
Sure.
Kelvin's great because it's a direct relationship to the amount of kinetic energy, and there's never any negative signs. Take it away, Mr. Mills.
All right, so another one. How about absolute zero? Wait, I made a mistake. Hold on, let me fix. No degrees in kelvins. If I have 0 kelvins and I want to convert that to Celsius, I'm going to have to subtract 273 from both sides. The Celsius temperature is now negative 273 degrees Celsius, which will equal 0 kelvins.
It's not okay. It's 0
No,
okay.
It's 0 K. Here, how about, is that better?
0 Kelvin.
0 kelvins.
So this negative sign here, you know how we hate doing math with negative signs. That's why the Kelvin scale was created in the first place, because
There's no such thing as negative energy.
there's negative. Right,
It has energy or it doesn't.
right, and that's why Lord Byron Kelvin. No, not Lord Byron. Lord Byron was a poet.
Yeah.
Lord Kelvin was a British dude that had something to do with creating this scale, temperature
Right.
scale.
It helps with our calculations.
Calculation. So, as a matter of fact, there's some practice related to this, and if you can use those that temperature conversion to do the practice, you just go ahead. Also, you got to have a fundamental understanding of how temperature and heat are related here.
Sure, they are not the same thing.
Yeah, they're not the same thing. And if you're having trouble, you got to do your keyword searches on heat, temp, temp scales, right? Maybe that'll help you out. If this video didn't help you understand that, heat, temperature scales, potential energy. What else could we search on? Kinetic, different types of energy.
You'll have to be careful with the kinetic and potential energy because you're going to get a lot of physics definitions on this.
Yeah, so maybe just do chem
Yeah.
and put in parentheses there, chem, okay? Because if there's anything I hope you've learned at this point, it's like, you got to learn this stuff, and if this isn't doing it, you got the internet to use
Seriously.
to jump to some other videos. I'm not going to be personally upset if a different teacher out there
No.
teaches you potential and kinetic energy in a better way,
By all means, come to us.
yeah, let us know. But I just care about you learning this stuff.
Right. And if
Any
you
way
have to go
necessary.
elsewhere, fine.
Fine by me. I'm not gonna take it personal.
No, not at all.
Okay.
See you guys.
Thank you.